So good morning, everyone. Thank you very much for inviting me to present today at today's symposium. It's been really great listening to some of the other guest speakers yesterday and also the student organizations yesterday as well. So in this talk, I'm looking forward to sharing with you some of the research that I've been conducting here at the University of Michigan. And it involves a comparison of display modality and human-in-the-loop presence for telerobotic on-orbit inspection of spacecraft. Now, this study was created in collaboration with MIT's Aero-Astro Lab, as well as NASA's Jet Propulsion Laboratory. This effort was also funded by a NASA award. So some very exciting things. Let me move this. Okay, so I'm going to start with a brief background about myself. It's something I know we've been talking about the last couple of days is how anyone can be in space. So I'd say my background's a little different than most, but I basically got my Bachelor of Science in human biology with a focus in applied physiology and a minor in psychology from the University of Michigan. So as a student athlete, I was very interested in human performance and injury mitigation. And then from there, I wanted to apply that to spaceflight. So I started attending some courses in engineering to beef up that background of mine. And then I ended up actually working at NASA's Johnson Space Center for a little over a year in the industry and had a great experience, being able to do quite a lot of research. So some of that is at the bottom of the slide here. I got to work on spacesuit fleet sizing, the neutral buoyancy laboratory, lunar operations development, as well as extravehicular activity injury, and then also spacesuit exercise device requirements. So that's some fun stuff there. So I'm going to jump into the background and motivation behind this current research. So as you know from the last talk, unfortunately, the Death Star isn't in this this video here, but exterior inspection of spacecraft is a crucial component to safe operations in space. And it's especially important for future long duration exploration missions that will require our astronaut crews to operate more autonomously. So naturally occurring micrometeoroids and man-made orbital debris, otherwise known as MMOD, is the #1 threat to spacecraft, satellites, and astronauts. Due to the International Space Station's orbit, the risk associated with MMOD is not trivial. So objects range from abandoned upper launch stages to fragments of satellite that have collided to tiny pieces such as flecks of paint, all of which are dangerous due to the speed at which they're traveling. So you can see kind of a good example of that in that center image there. You can get quite a bit of damage with that speed of objects. So overall, collision with orbital debris can damage spacecraft and mission critical structures, such as solar arrays, and in worst case scenario can lead to catastrophic failures such as depressurization. Now, current inspection of the International Space Station is done through extravehicular activity, otherwise known as EVA. And EVA efforts are costly. They subject our astronauts to a great deal of risk, and they require quite a bit of oversight from mission control. So due to advancements in robotics, small free-flying vehicles have become a viable alternative to on-orbit inspection and maintenance. To date, several free-flying vehicles have been demonstrated in flight with crew members on the International Space Station. So there's a picture there of, they're called Astro Bees. So pretty exciting systems there. Now, in terms of the study, we wanted to figure out how our astronauts would interact with these robotic systems. So teleoperation remains the predominant control paradigm for humans interacting with robotic systems, particularly in space environments. So some examples of teleoperated space-specific robotic systems include the International Space Station's remote manipulator system, otherwise known as the Canadarm2, and then also a very relevant Mars Perseverance rover. So teleoperation is usually achieved through the visual display and control interfaces. Therefore, we wanted to consider telerobotic inspection from an interface perspective, where we compared 3 different visual displays. So we have 2D, 3D, and augmented reality. We also wanted to consider the research from a mission operations perspective. So understanding the degree of human synchronicity with the inspector robot is crucial for mission planning. So there are 2 scenarios here. We have a synchronous human robotic control, where the astronaut would actually be flying the robot themselves in real time around the space station inspecting. And then the other end of the coin would be asynchronous review. So in this case, the robot would be fully autonomous and they would basically fly around the station, capture video data, and then the astronaut would then in post review this data for inspection. So those are kind of the two independent variables that we're looking at: interface design and human synchronicity. So to understand any complex human-machine system, we must address human information processing and decision-making. So due to the operator's remotely located position relative to the robot, natural human processing abilities are decoupled from the physical environment, posing considerable challenges to an operator's situation awareness. And situation awareness is basically the understanding of information, events, and actions that impact mission objectives in dynamic environments. Now, situation awareness is usually defined in 3 different areas. So we have perception of kind of objects within the state, comprehension of the current state, and then also projection of future states for short-term planning. In the context of teleoperation with robotic systems, the operator must perceive the vehicle parameters such as speed and location relative to the environment, comprehend the significance of the situation, and further project for decision purposes. So the maintenance of the operator's situation awareness through appropriate interface design is important to effective teleoperation of robotic systems, particularly in space operations where poor navigation can damage mission-critical hardware. So this brings us to extended reality technology. So we're very interested in incorporating novel forms of visual feedback to support an astronaut's situation awareness while navigating around the space station. So extended reality has been a very awesome form of technology that has allowed some good interaction with 3D models between humans and robotic systems. So I wanted to give a brief overview of extended reality in human spaceflight that's currently, been happening over the last couple of years. But basically, you have pre-flight operations and post-flight operations. So we have astronauts rehabilitation as well as training, and then also in flight for mission operations. They recently flew the Microsoft HoloLens 2 on the International Space Station for, research purposes and also some other, procedural work. So exciting things there. But ultimately, what we wanted to see is if we could implement AR and if it would be beneficial in inspection operations. So I'm going to talk through, this was the experimental setup here. So what we have is a dual monitor setup. The left monitor was the egocentric view, so it's the perspective of the robot. And then the right monitor is what differed per modality. So what you see here is currently the 3D interface. I'll walk through the other ones a little bit later, but I did want to show you kind of our whole setup and what our participants were interacting with. In terms of control, what we have is a keyboard, a mouse, and a joystick. So of course, the joystick helps fly the robot during that synchronous control. And then all the interfaces kind of use a combination of some of those controls. And then what you see at the left is the AR headset. We use the Microsoft HoloLens Generation 2. All right, so I'm going to walk through our interfaces. So starting with the 2D interface, you can see on the top row, we have the synchronous, and then the bottom row is the asynchronous inspection. So during synchronous inspection, our participants would basically fly the robot. It was constrained to a single plane. So what we had them do was inspect just basically the circumference, but they were allowed to pan the camera up and down. So I'll just show a quick little video here of that 2D interface. And so for the 2D, again, that right monitor was 4 fixed cameras on the exterior of the spacecraft. And it's important to note that this did not provide a comprehensive view of the space station. That's a quick example of that. You can see an anomaly right there, kind of at the top. It's moving pretty fast, but okay. So the next one would be the asynchronous review. And the only thing different here is the left monitor is now basically like a video playback. So again, the robot had gone through a full inspection without the operator, and now the operator is reviewing that imagery in post. All right. So moving on to the 3D interface, what we have here is the same egocentric view on the left. And then on the right, you actually have, I'm sorry, it's so dark. I'm not sure why it's that dark, but basically it's a CAD model of the space station, and it's interactive. So it allows the participant to move around, change the viewpoint to assist with navigation as well as anomaly inspection. So the anomalies were visible on this 3D CAD model, which is quite helpful. So I'll let that play for a little longer. And then for the asynchronous review, what you have is that same CAD model, but it's now just on the left screen. And so our operators would just manipulate, detect anomalies there on that screen. Okay, so the last one would be the AR interface. Here's a fun video of me manipulating the holograms. So it's a pretty cool, unique system where you can actually see the spacecraft as well as the robotic satellite there. And again, in the synchronous control, the operator would be using that joystick to fly the robot. And that hologram basically replaces that right screen to allow them to just give them views and the flexibility to change the viewpoint as they like. For the asynchronous view, what we have here is 2 holograms. So one thing that I wanted to note is that red box, looks like a Windows icon, is actually how we had our participants document anomalies. So that red box was actually visible in all interfaces. So it's just here to show you kind of what we had them do is resize that bounding box, place it over the anomaly to capture a picture of the anomaly. So there's that. Okay. So talking about our research objectives, we wanted to understand how operators were utilizing the interface and how effective this utilization was in the completion of task goals. So the task goals included inspection of the entire circumference. So again, they were constrained to a single plane. We wanted them also to avoid collisions with the space station. So we asked that they tried to maintain a 2-meter distance from the space station with the robot inspector. And they basically had 15 minutes to complete inspection in each interface and condition. So in terms of hypotheses, I know this is a lot of words on the slide, but I'll walk through them pretty quickly, is for the AR and 3D interfaces that featured those interactive 3D models, we hypothesized that this would lead to better clearance, so that maintenance of that 2-meter distance between the inspector and the space station. We also said that it would enable a higher percentage of the space station to be inspected, and then ultimately lead to greater anomaly detection, because they had just more freedom to have more viewpoints to see those anomalies. We also expected that these session lengths would be a little bit longer because they would be spending time manipulating those viewpoints on the right. In terms of synchronous inspection, we thought that the participants would employ both control modes. So again, they had the ability to fly in automatic mode or manual mode when they're flying that robot. So we thought they would kind of use a combination of both to optimize performance. For the between tasks, so between synchronous and asynchronous, we thought that the synchronous anomaly detection would be superior. And this is because the operator is present and their attention is fully engaged in navigation as well as inspection. So some of the metrics that I'm trying to play this video here. We're not, okay. I guess the video will not play for me, but basically, I'm sorry, why is that not working? Oh, there we go. Nope, never mind. All right, so no video. Nope, there we go. Okay. All right, so what we looked at were inspector metrics such as inspector speed, path length, and the mode, as I talked about. So we had automatic mode, manual mode, as well as picture mode, and other performance metrics like anomaly detection and session length. So what we created was a super helpful analytics GUI, basically. And what it helped us do is visualize these user strategies. So you can see in the right, the path length, when they stopped, what control modes they used. And also I could kind of go through the pictures that they took to see if they were correctly detecting anomalies. So now to go through the results, starting with anomaly detection performance, and basically session length. So what we found is that the 2D interface yielded faster session lengths. So this was to be expected because they basically were not interacting with that right view. They would maintain with that egocentric inspector view. Now, surprisingly, the 2D interface resulted in superior anomaly detection in the synchronous inspection case as compared to all the other combinations. So again, this was very surprising, not what we expected, but interesting nonetheless, because this has very important implications in how we want to design these robotic systems in the future. For navigation, specifically navigation came into play for that synchronous case. And what we have is that the 2D interface yielded faster average inspector speeds and less idle time. So basically the less time that the inspector was stationary. So this again is not only did they have better performance in anomaly detection, but they actually flew faster and kind of just did the task a lot faster in that 2D interface. We did note that you can see in that right graph to the far right is that participants actually exercise more caution while teleoperating the inspector with that 3D interface by a larger average minimum distance. So this provides some support for our hypothesis that the 3D interface would allow for just better navigation and collision avoidance. In terms of control mode, we did some k-means clustering to yield 4 comparable strategies. And so you can see on the graph, we have automation versus manual mode. And so what we have here is 4 strategies for the 3D and AR interface and a 5th strategy for the 2D interface. So if you take some time to look through, I know it's kind of busy, but those numbers basically correspond to the subject number. And then you can see that quite a bit of subjects actually did not use automation mode at all. And then some actually used it as much as they could. So that's those green groups and the pink groups. And so what's important to note here is we found some interesting, if you look at the numbers, these subjects actually maintained their inspection strategies across interface. So that was interesting. So they either stayed in the same cluster or were adjacent, a cluster adjacent for the next interface. So, one thing to note, I totally forgot, was basically this does support our hypothesis in that we assume that the majority of our participants would use the automation mode as well as manual mode, kind of a mixture of both to help with performance. So we do see that with the majority of the subjects kind of in those center 2 blue and red clusters. Now, the subjects who did not use automation mode said that the manual mode was simply more fun to manipulate than others. So we get that it is more fun to, fly a robot around yourself. We also had some subjects say that the automation moved too fast for kind of their inspection. And so implementing adjustable automation speeds may shift this command mode strategies by encouraging greater automation use and also improve proximity maintenance as a secondary response. So in terms of subjective ratings, we wanted our subjects to kind of give us their perceived kind of demands. So we use the NASA TLX, which is the Task Load Index survey. And what we found here is there was only a significant decrease in the mean perceived physical demand while performing the synchronous inspection. Now, we did not decompose by interface in this case, so it was just synchronous versus asynchronous. And so we think there was quite a bit of influence from the AR interface for that higher perceived demand in the asynchronous. And this is because they were manipulating 2 holograms at the same time, and it led to some arm fatigue. But it is important that this would not be a consideration in microgravity. Other subjective ratings, we were interested in seeing if there were any portions of the space station that were hard to inspect within a given interface. And what we found is that space station features that protruded in the zenith and nadir directions were reported as challenging across interface, but especially for that 2D interface. So if you remember, for that 2D, it was just those 4 fixed cameras. So again, it's very hard to kind of comprehend some of that space station structure. We also had our subjects give subjective ratings on their preference of interface. So what we found is that 79% of our subjects chose the AR interface as their preferred interface. And again, this could be just because it's a novel and fun technology. So that could be kind of one of those effects there. We also found that the next preferred interface would be the 3D interface. And then lastly, no participants listed the 2D interface as their preferred interface, which was again very interesting because their performance did not support this. So again, they perform better in that 2D interface. Now, reasons for their top choice were better spatial awareness, ease of identifying satellite location, collision avoidance, and basically understanding how the satellite will respond to input. So we saw some support of this again with that kind of collision avoidance and average minimum distance in that 3D interface. But again, it's just mixed support there, not fully supported. So in terms of key points and takeaways from this, what we have is the interface. From an interface perspective, we recommend that varying commands should be, well, we found those different command strategies. So we recommend for future human-in-the-loop teleoperation interfaces necessitate flexibility in automation and command capabilities. For the measures that we analyzed, the results did not suggest a benefit of AR over the 2D egocentric view. So basically in the current implementation and in these results basically recommend that AR is unfortunately not helpful in a interface design perspective. From mission operations planning, when applicable, operations should include synchronous human-in-loop presence for telerobotic on-orbit inspection of spacecraft. In terms of limitations, the study did not evaluate, again, the movement was constrained to a 2D plane, so it did not evaluate the full 3D space. We understand that 3D and AR implementations may prove to be more helpful in these 3D configurations. We also recognize that our subjects were allotted 2 hours of training on the system 1 day prior to evaluative testing, but we acknowledge that basically other analogous systems require quite a bit of training. So understanding and future research on some of these 2 aspects would be interesting to consider. So in terms of future research, what we have kind of lined up is we are implementing the simulation software at NASA's HERA facility. So it's the Human Exploration Research Analog. And I don't know how many of you are familiar with that, but basically they usually put 4 crew members in for extended mission, so about 45 days. And so what we're going to see here is if operators' strategy changes over time as they get comfortable with the system and use it for regular inspection operations. What we're also doing on the flip side is going off of the simulation software and bringing it to real robotic software. So we're going to have a space station mock-up and a drone, and we're going to see if AR is helpful in a real life scenario. So even though we did not see AR as a helpful implementation here in inspection, there are other exciting things happening with AR. So for example, intravehicular assistance, heads-up display for spacesuit architectures, and training capabilities for ground operations. So I just want to give some quick acknowledgements to my colleagues and mentors. So Dr. Leah Stirling of the University of Michigan, Dr. Andrew Liu of MIT, Amos Bayon and Jonathan Blossom from NASA's Jet Propulsion Laboratory. So I know I went a little over there, but thank you very much for listening. I appreciate all your attention, and I'm ready to take questions. I can't hear anyone. Let's see.
Sorry, I was muted. I'll go ahead and ask the question that was thrown in the chat earlier. Can an exterior robot connected to an AR/VR system improve inspection? And is there any robot in the ISS now doing so?
Okay, wait, so can an exterior robot connected to it? Okay, yeah, so what we found is that in this implementation, AR it was not helpful. So this could be that we did just basically find that when our participants focus mainly on that egocentric view, it was sufficient in allowing them to basically inspect with good performance. Now, it's important to note again that the AR could be beneficial if we had, more complex space structures and if we had our participants fly in full 3D space. So we think AR could be implemented for better navigation, but again, for the measures that we saw here is that we did not see help with that. And is there a robot right now? So I did show you kind of those intravehicular way in the front. So they're the Astro B robots, and basically they were just helpful for procedures on the International Space Station. Looks like my screen will not go back. Come on. Okay, so these guys down here, so they have been flown in flight on the International Space Station, but there are currently no robotic systems that we were testing that would be flown outside of the space station just yet, but that will be coming soon.
Awesome. If anyone has any more questions, feel free to throw them in the Slack, or not sure if you prefer them to email you.
Yeah, either way, I'm happy to answer any way you can get contact.